Hi everyone. So in the last video I introduced finally Einstein's field equations. Okay, so these are the big equations of general relativity, and so on the right hand side here we have the energy momentum tensor, just to remind you, and it's the tensor that describes the distribution of mass or energy that generates the gravitational field, so to speak. And then on the left hand side we have this kind of arbitrary looking combination of things. So this part is the Ricci tensor, this is the metric tensor, and this is the Ricci scalar. Together this combination is called the Einstein tensor. It's a rank 2 symmetric divergenceless tensor, as is the energy momentum tensor. And anyway, this bit on the left hand side is the tensor that describes the curvature of space-time due to the mass or energy that's in the energy momentum tensor. And so when you try to solve Einstein's field equations, what you're doing is you're given a distribution of mass or energy first, so you're given an energy momentum tensor, and you're trying to find the so-called gravitational field it generates. So what you do is you solve this equation for the 10 independent components of the metric tensor. And these equations, although they don't look like it, I tried to explain last day that they are a set of 10 second order nonlinear differential equations for those 10 independent metric tensor components. Okay, and so because it's a second order differential equation for the components of the metric tensor, it is analogous to Poisson's equation in Newtonian mechanics, Newtonian gravity, where you have a second order linear differential equation for the gravitational potential related to the mass density. But at any rate, before we actually think about some examples of solutions to these equations, so actually solving a specific example of a mass distribution to get the metric tensor, before that we want to look at just a couple of other things just in general. And the first thing is the vacuum field equations. Okay, so if you're in a region of space where there is no matter, okay, no mass, then you're in a vacuum, and in that case these equations actually simplify quite a fair bit. Okay, so we're going to see that now, and actually in what we're interested in, that is going to be the case. Okay, so really we're going to be thinking about a situation where you have a star like the sun that generates the gravitational field, and then you'll have a planet moving in the gravitational field. Okay, that's really what we're going to come on to. But that planet is moving in a vacuum. Okay, so yes, the sun is there and the sun is generating the gravitational field, but the planet is outside of the sun. Okay, the planet is, if it's the Earth, it's 92 million miles away. So the planet is in vacuum. Okay, so it can still feel the gravitational field, so to speak, of the sun is there, but you're outside the actual mass material that makes up the sun. So that's vacuum, where the Earth is. And so actually then, rather than thinking about these full field equations, which are valid inside the sun itself or outside, we only need to use the vacuum field equations. So let's see how we can find those. Now, before we actually do it, what we're going to do is take Einstein's field equations as they are written here, and we're actually going to rearrange them slightly. Okay, we're actually going to come up with an alternative form of the field equations. So if you take this one, okay, so I've written the field equations in 3 forms again, so fully contravariant form, fully covariant form, or mixed form. But let's take the mixed form and let's set the 2 indices, mu and nu, equal, and then sum over them. Okay, so contract these indices. So contract mu and nu here in the mixed form. So we will have r mu mu, let's just set mu and nu equal, so r mu mu, let's say, minus a half g, sorry, not g, it's a delta in the mixed form, Kronecker delta, mu mu, r equals minus kappa t mu mu. And kappa here, remember, is just this constant of proportionality for now. We will talk later in this video about what it actually is, but for now it's just an unknown constant. Okay, and so what next? Well, we can actually find what delta mu mu is quite easily. Okay, so remember the Kronecker delta, if the 2 indices on it are different, then it's 0. If the 2 indices are the same, then it's 1. Now in this case the 2 indices are the same, so it's 1, but they're summed over. Okay, so remember here, repeated index, mu upstairs, mu downstairs. Einstein's summation convention says you sum over this index, and remember it's 4-dimensional space-time. Okay, so these, the mu and the nu, remember, they denote the coordinates. So you've got x0, x1, x2, x3. Those are the coordinates of your 4-dimensional space-time. The same as in special relativity. So in fact, this delta mu mu is 4. Okay, because yes, the top and bottom indices are equal, but then you sum over the mu's, and there's 4 of them, so you actually get 1 plus 1 plus 1 plus 1, which is 4. So we get r mu mu, and then minus a half of 4 is just 2, so minus 2r is equal to minus kappa t mu mu. But look carefully. Here we've got r mu mu summed over mu, and here's r. Those are the same thing. Okay, remember, that's the definition of R. R is the Ricci scalar. And how do you get the Ricci scalar? You take the Ricci tensor, rank 2 Ricci tensor, in its mixed form, and contract the indices. So R mu mu, that by definition is just R. So on the left-hand side here, you've actually just got R minus 2R, which is minus R. So if I multiply 3 by minus 1, I just get R equals kappa T mu mu. Okay. Now, what I can do is I can take this this identity that I have found, and I'm going to put it back now in here. So I'm going to take, I can take either the contravariant form or the covariant form now of the field equations, doesn't matter. But at any rate, I will get the following. So R mu nu, I keep that, minus a half G mu nu, and then R here, the Ricci scalar, I'll replace with this. So you've got kappa T. Now I have to be careful with indices. So here I've got mu mu, but it's just a dummy index. It's summed over. Now I've already got mu here, and here it's a free index. So let me rename this to something else, this dummy index. Let me just call it alpha alpha, say. But it is summed over. And then on the, where am I? Yes, on the right hand side, then I have equals minus kappa T mu nu. All right, and let's rearrange so that we just have on the left hand side this R mu nu, okay, Ricci tensor. Let's bring this term over here. That minus sign will become a plus. I've got a common factor of kappa, so let me bring it out like this. So I'll have minus kappa times T mu nu plus this thing, so plus a half G mu nu T alpha alpha. Okay, have I done that right? Minus kappa T mu nu plus a half G mu nu kappa T alpha alpha. Yes, I think that's okay. And okay, this here now is just an alternative form of the field equations, okay? So it's not the vacuum field equations yet, okay? It's just an alternative form of the full field equations. But this now will give us a very big simplification when we assume that we are in a vacuum. So in a vacuum, so in other words, in a region of space where no mass is present, the energy momentum tensor is 0 at that point. Okay, so T mu nu is 0, and T alpha alpha there, that's also 0. So the whole right hand side just goes to 0. So in a vacuum, Einstein's field equations just become R mu nu equals 0. Okay, and that's the vacuum field equations. Okay, much simpler. Okay, so it's just Ricci tensor equals 0. Okay, now the last thing I want to say then in this video is just a little bit about this constant kappa. Okay, so now just going back to the full field equations now. Okay, so not just the vacuum field equations. Now going back to the full field equations, and I want to say a little bit quickly about kappa. And as I say, it is a constant, and Well, there are two approaches here, really. On the one hand, you could just say, okay, kappa is just a new universal constant. Go do some experiment, or go measure the motion of planets or something in some way and just get a value for it by experiment, and that's it. You could do that, but we already have a universal constant for gravity. And yes, to be fair, it comes from Newton's theory, but still, it's there, and it's called big G, and it has a certain value. And it turns out that you can, rather than letting kappa be a brand new constant, you can relate it back to the old Newtonian gravitational constant G. Now, how do you do that? You require that Einstein's field equations, in the limit of a very weak gravitational field, it goes back to Newtonian gravity. Okay, so remember, Newton's theory of gravity was around for a long time, okay, hundreds of years, before anybody really realized that it wasn't quite right. Okay, so although it's wrong, although Newton's theory is wrong, it still does a pretty good job, right? It's a pretty good approximation most of the time. It starts to break down when your gravitational field gets pretty strong. Okay, that's when you start to notice errors in it. In particular, well, I said hundreds of years a second ago, but actually, I think even in Newton's lifetime, they knew there was something just not quite right about Mercury's orbit. Okay, so Mercury is the closest planet to the Sun. Therefore, it's in the strongest gravitational field, and when you watch its orbit, when you look at its orbit, it doesn't quite agree with what Newton's theory says it should. Okay, that's true for all of the planets, but especially so for Mercury, and they were able to observe that even at that time. So, still then, Newton's theory is a good approximation when your gravitational field is not too strong. But the stronger the gravitational field gets, then the worse Newton's approximation becomes. So, at any rate, we can relate this constant kappa back to Newton's old gravitational constant G by taking a weak field approximation. Okay, so we require that in the limit of a weak gravitational field, that Poisson's equation for Newtonian gravity really drops back out from here. Okay, so I'll write here, how do you find the constant kappa? We require that Einstein's theory of gravity reproduces Newton's theory in the weak field limit. Okay, now in your PDF notes, I have done a very extensive section with all of the maths here of doing this and all the derivations. Okay, it's kind of long, it's complicated, but there are two key results. Okay, so the first result that kind of drops out for free is the following. So remember what we're doing in Einstein's field equations. Remember what we're doing? We're trying to solve them for the metric tensor, okay, for the 10 independent components of the metric tensor. Now, when you take this weak field approximation, so if your gravitational field is not too strong, it turns out you can find that the 0,0th component of the metric tensor is approximately minus, open brackets, 1 plus 2 phi over c squared, where phi here is your Newtonian gravitational potential. Okay, and that really hammers home, I hope, this idea that the metric tensor is analogous to the gravitational potential. Okay, so there's a very important direct relationship between the two that becomes evident in the weak field limit. Okay, but the more key result here is about the constant kappa itself, and it turns out that kappa is 8 pi g over c to the 4. Okay, so c here is the speed of light, and g here is your Newtonian gravitational constant. The details of where this and this come from are in the PDF notes. Do you have to know it, like for the exam, for the test? No. It's long, it's difficult. I wouldn't expect you to be able to reproduce it. or if I did ask you something about it, I would certainly give you all the information that you needed to do it as an unseen problem at least. But that now is Einstein's field equations in full, really. So we've got the kappa, we know what it is now. It's still just a constant, but it's 8 pi g over c to the 4. And that's true, by the way, even not in the weak field. Okay, you find this constant by taking the weak field limit, but it's a constant. So it still stays that value for a weak field or a strong field in the full field equations. So we've got the kappa. We've also got a formula for the 0,0th component of the metric tensor if it is a weak field in terms of the old gravitational potential. But most usefully, perhaps, we've got the vacuum field equations. Okay, so in a region of space where there is no mass, okay, so you may be in a gravitational field that's being generated by a mass distribution nearby, but if you're outside of that mass distribution, okay, like the way a planet would be when it orbits the sun, it's not inside the sun, it's outside and orbiting, then you don't need to solve the full field equations, you just need to solve the vacuum field equations, okay? Solve them for the metric tensor. And in the next video, what we're going to look at is one specific solution of the vacuum field equations, and it's the case where, as I've mentioned, it's the case where you have a gravitational field generated by a star just sitting there, okay, so it's just a non-rotating spherically symmetric star, and the solution, there's a special name for the solution, it's called the Schwarzschild solution of the vacuum field equations, okay, or just the Schwarzschild metric. So we're going to look at that next time, and then we're going to look at, once we've got the solution, once we've got the metric tensor for the Schwarzschild solution, we're going to look at motion of planets, motion of objects in that curved space-time described by that metric.